in this question we have to show that it is a linear transformation. So we have a mapping here. They have given you the mapping T from XYZ. T is a mapping from R3 to R3 defined by T XYZ is equal to X plus Y plus Z, comma Z plus X is a linear transformation. So we have to show this mapping is a linear transformation. Okay, so what is your mapping? The mapping is from where? From R3. We have a mapping from R3 to R3. Okay, so we have a mapping from R3 to R3. Okay, so how we have defined X, Y, Z. I take one element in R3. This is defined to be X plus Y plus Z, Z plus X. And we have to show this is a linear transformation. Okay, we have to show that this is a linear transformation. So I'll take two vectors in R3. So the vectors in R3 will be three tuples. Okay, so I take two vectors, x1, y1, z1. This is one vector, and another vector I'm taking as x2, y2, z2. So this is in R3. Okay, this I take in R3. So I'm taking two vectors in R3. Okay. So I've taken two vectors in R3, and I'll take one scalar in the field F. So I take one scalar in the field F. Take one scalar in the field F. So here the field is real number. Okay, so the field here is real number. So the first condition of linear transformation, I'll try to prove the first condition. I'll add them together. So we have x1, y1, z1 plus x2, y2, z2. So this will be equal to, what we'll get? If I add this 2, I'll get here. If I add this 2, I'll get as x1 plus x2, comma, y1 plus y2, comma, z1 plus z2. Okay, so this way we have to add coordinate wise. Now this you think as your x, this you think as your y, and this you think as your z. Okay, so by the definition here we have x plus y, so this plus this. Okay, we get here x1 plus x2 plus y1 plus y2, comma, y plus z. So this plus this. So we have here y1 plus y2 plus z1 plus z2. Then we have here z plus x. So we have z1 plus z2 plus x, means z1 plus z2 plus x1 plus x2. We have here z1 plus z2 plus x1 plus x2. Okay, so we have this. Since these elements are in R3, R3 is a vector space under R3 is a vector space, so it is an abelian group under addition, so we can interchange this. Okay, if it is not an abelian group under addition, we cannot do that. Since it is an abelian group under addition, we can interchange it. So we have here x1, because these are all elements of real numbers. Okay, also this part, this is an element of real numbers, this is also an element of real numbers, this is also an element of real numbers, and R plus is an abelian group under addition. Okay, so we can interchange this. We have here x1 plus y1 plus x2 plus y2, comma, y1 plus z1 plus y2 plus z2, comma, z1 plus x1 plus z2 plus x2. So we have this. So this can be written as, we can write this as x1 plus y1, comma, y1 plus z1, comma, z1 plus x1, plus coordinate wise If we add, we get the same thing as above. X2 plus Y2, Y2 plus Z2, and here we can write as Z2 plus X2. So this is equal to, this is nothing but, if we reverse back the definition backward, if I reverse this definition backward, this was XYZ. So if I reverse back this definition, this will be nothing but, it will be T X1 Y1 Z1 plus T X2 Y2 Z2. Now let us check the second condition. So we have T alpha on applied on X1 Y1 Z1. So let me multiply this alpha inside. So we get here T alpha X1, alpha Y1, alpha Z1. Now this is your X, this is your Y, this is your Z. So using the definition here, we'll have here alpha X1 plus alpha Y1, comma, then we can have alpha Y1 plus alpha Z1, comma, alpha Z1 plus alpha X1. So you can take alpha common. So if I take alpha common here, I get alpha X1 plus Y1, alpha Y1 plus Z1, and alpha Z1 plus X1. So alpha is constant, it will come out. So we get alpha X1 plus Y1, Y1 plus Z1, comma, Z1 plus X1. Okay, so if I reverse the definition according to the definition, this X plus Y, Y plus Z plus, comma, Z plus X is T of X, Y, Z. So if I use this definition here, okay, if I use this definition here, we get alpha T of X1, Y1, Z1. So this T satisfies both the condition, therefore T is a linear transformation. We have shown that T is a linear transformation. Here also, so we have this question. Let F from R3 to R3 be a mapping defined by F of x1, x2, x3 equal to x1 minus x2, x2 minus x3, x3 minus x1. So we want to show that this is also a linear transformation or linear mapping. Okay, linear mapping is nothing but a linear transformation. So to show it is a linear transformation, you always take two vectors from the domain. So here is R3, so the vectors here will be tuples, three tuples. So I'm taking here three vectors, two vectors here in R3, and the field is real number, so I take alpha belongs to R. So we'll try to add these two. So we have this, we have to add coordinate wise, so we get x1 plus x1 dash, x2 plus x2 dash, comma, x3 plus x3 dash. So this is your x, this is your y, this is your y, and this is your z. Or this you can take as x1, this is your x2, this is your x3. So by using the definition, here we have x1 minus x2, means this minus this, then this minus this, then this minus this. So I'm using this here. Then we get, you can multiply this minus inside. So these are all elements of real numbers. So it is an abelian group under addition. So we can commute this. So we have here x1 minus x2 plus x1 dash minus x2 dash, x2 minus x3 plus x2 dash minus x3 dash, plus x3 minus x1 plus x3 dash minus x1 dash. So we can separate this in two coordinates. So we get here x1 minus x2, x2 minus x3, x3 minus x1, x1 plus x1 dash minus x2 dash, x2 dash minus x3 dash, comma, x3 dash minus x1 dash. So this, okay, this is equal, if we use the definition back, this is nothing but f of x1, x2, x3, and this is f of x1 dash, x2 dash, x3 dash. So this we get here, this is equal to sorry, here we have a mapping here. This is your f. Okay, this is your f, so this will be your f. It is not x, it will be f. So this will be f. Okay, this will be your f. Okay, so this is f. In the same way, here also we'll have here f. This also will be f, and this also will be f. So here we have f of alpha x1 comma x2 comma x3. So you multiply this alpha inside, so we get alpha x1, alpha x2, alpha x3. Now using this, you think as x1, this you think as x2, this you think as x3. So we have this minus this, the comma this minus this, comma this minus this. So we are using that way. You take alpha common, here also take alpha common, from here also take alpha common. So we get this. Now we can take throughout alpha out. So we get here this. So this is nothing but f of x1, x2, x3. And this, so here we have f. So f is a linear transformation. So in the same way, you can do this as your homework. So that is, let f from R3 to R3 defined by, this is your definition. You have to show that this is a linear transformation. Thank you.